Hi, welcome back to the Math Studio. We're going to be looking at more vector problems here. So let's get right to it. When you have two vectors that are in component notation, you can easily add them or subtract them by just adding or subtracting their individual components. So this is just a quick, easy way to add or subtract vectors. You just add the components together. Multiplying by a scalar is also pretty easy. If you want to multiply a vector by a scalar, if it's in component notation, you just multiply each component by that scalar. That's what this diagram is trying to illustrate for you, is that multiplying by c, you just multiply each component by c. So this is from your book, but it illustrates the same thing. You have several different formulas here, but essentially the idea is that if you want to add or subtract vectors, you just do it one component at a time. When you want to multiply a vector by a scalar is just a number. You know what? I just realized I'm using this word, and you might not know what I'm saying because I have a weird accent. I'm not from Ohio. Here, this is the word scalar. There, scalar. So I pronounce it like this, scalar. Okay, but this is the way it's spelled, scalar. So a scalar is a number, as opposed to a vector. Okay, just want to make sure we clear that up because I just realized I'm using this word. I want to make sure you know what I'm saying. If I ever say something that you have no idea what I'm saying, let me know. Send me email. Okay, so getting back to this, pretty straightforward. Multiplying by a scalar by a vector, you just multiply components. You can extend this to multiple dimensions. If you have a three-dimensional vector, uh, then you deal with three components. N-dimensional vectors would have n components. So we aren't going to deal with those in here, but if you got linear algebra, you might have this sort of thing. There's a few other properties of vectors. These are in your book. They aren't all that exciting, but one thing to note is that everything works as you would expect it to, in the sense that adding and multiplying, or we're just adding here, adding is commutative. You have an associative property, that's number 2. There's an additive identity. By the way, that zero, the zero vector, that's just a bunch of zeros. You can distribute a scalar, like C can be distributed. This is number 5 up there. As well as you can distribute a vector. That's number 6. And then there is a multiplicative identity, the number 1. So all of this is non-surprising, hopefully, um, as we move forward. Onward, we have some standard vectors. These are some special vectors. These are called the standard basis vectors. They all have length 1, and they point in the directions of the x, y, and z axes. So the reason why these are helpful is because there are going to be times when writing our vectors in terms of these special vectors will be preferable to writing them in component notation. Let me show you what I mean by this with an example. Well, at least show you what I mean by writing these things out. So let's say I have this vector. That is the same as 3 times the vector 1, 0, 0, plus 2 times the vector 0, 1, 0, plus 5, need more room, times the vector 0, 0, 1. So first thing you have to agree with me is that that's correct. All of that is basic arithmetic almost with a few vectors thrown in. Anyway, using the notation that I have up here, we're going to call this 3i. This is going to be 2j. And this is going to be 5 times k. Like I said, there are going to be times when doing calculations with vectors are a lot easier if you write it in standard basis notation as opposed to component notation. Just to illustrate this one more time, let's say I have this vector, -5, 0, 4. that is the same as negative 5i plus 0j plus 4k. So I could write this down without having to copy down all of this mess that I have up here. Not only that, since there's 0j, I can write it this way. And there's nothing wrong with that. That's the same exact vector. All right, so moving on. My standard basis vectors can be represented on the Cartesian coordinate system like this. So you have the vector I in 2 dimensions points along the x-axis, the vector j points along the y-axis, and then in 3 dimensions you also have the vector k pointing along the z-axis. Not all that surprising or difficult. We already talked about this and we've done some examples, so we're going to skip that. Yeah, we don't need that either. Okay, onward. Unit vectors are vectors that are 1 unit long. So once we have a vector, we can turn it into a unit vector by dividing by the magnitude of the vector. So and once again, this is going to be convenient at times to be able to come up with a unit vector that points in the same direction as a particular vector. And so let's do this with my vector that I have here. Actually, both of the vectors. Give me a sec. So we'll start with that one. So you can see, oops, well, there it is. So let's get a unit vector that points in this direction. To do that, if I'm going to, let's see, I'll call this vector v. So the magnitude of v is using the distance formula, 3 squared plus 2 squared plus 5 squared. And that's going to be what, 13 plus 25, which is the square root of 34. And so my unit vector that points in the same direction as the vector v will be 3 over radical 34i plus 2 over radical 34j plus, ooh, you know what? Did I make a mistake there? I did. Let me do the math, because apparently I can't do math in my head. Let's see, this is 9 plus 4 plus 25, which is 38. Okay, I apologize. Let's fix this. Okay, at any rate, you still get its similar idea. Divide by the magnitude, and this will be a unit vector. That is to say that this vector points in the same direction as v, but this u vector is 1 unit long. So that's the point of a unit vector, is you have a vector, it points the same direction as your vector, but it's only 1 unit long. Let's do the same thing for this vector. So I need the magnitude, we'll call this vector a. And so the magnitude of a is the square root, oh, you know, I don't know what I'm doing here. That, you know, this is the problem with doing this on a video. I'm not going to fix that. And I know that you were looking at that going bonkers. And I didn't get the feedback because I can't hear you from where you are. Well, it's the way it is in this coronavirus, right? Well, let's go ahead and do this anyway, now that I've fixed that. Yeah, you saw that. I know everyone saw that mistake. So sad. Okay, anyway. So let's see. The magnitude of this vector is this plus this, which is the square root of 25 plus 16, which is 41. And so that means that a unit vector that points the same direction as A would look like this. Whew. My apologies. I hope that didn't cause you any stress or strain. Well, I feel like I need a break. You probably do too. Let's pause and then we'll come back for the examples in the next video.